I began to seek the foundations of physical reality, I knew I had to explore fundamental physics. And when I began to explore fundamental physics, I knew I had to look through the prism of mathematics. I focused on an essay by the mathematical physicist Eugene Wigner, whose iconic title spawns deep reflections on the nature of reality, the unreasonable effectiveness of mathematics and the natural sciences. Wigner's first point hooked me. Why do mathematical concepts make entirely unexpected connections? Why do mathematical equations produce unexpectedly accurate descriptions of natural phenomena? Wigner calls this usefulness of mathematical concepts uncanny. Uncanny? Why uncanny? Why do math's explanatory powers seem so mysterious, so magical? Why the unreasonable effectiveness of mathematics? I'm Robert Lawrence Kuhn, and closer to truth is my journey to find out. As I hear Wigner's arresting title, The Unreasonable Effectiveness of Mathematics and the Natural Sciences, two concepts stand out as obvious drivers: effectiveness and unreasonable. The two concepts differ. Effectiveness seems more a factual question. I've assumed the effectiveness of math, but does it stand up to scrutiny? Unreasonable seems a more value judgment. Aren't math and science supposed to be reasonable? Does unreasonable apply hidden knowledge, deep secrets? I explore both, each in its own way. I begin at the Institute of Advanced Study in Princeton, New Jersey. I meet its director, a mathematical physicist with broad vision in science, Robert Dijkgraaf. Robert, Wigner's famous comment about the unreasonable effectiveness of mathematics. I understand the effectiveness of mathematics, but why is it unreasonable?
I think it's unreasonable to expect that a piece of mathematical technique will appear again and again, and often in places where we do not expect it, like periodic motion, the orbits of the planets, the math that came along with that. You can also apply it in atoms, in analyzing sound, even in fluctuations in economics. Wigner, in his essay, even makes the remark that all of these applications underlying is the circle. In many mathematical formulas, you see the Greek letter pi, which actually is about the ratio of a circumference and diameter of a circle. But often it's not at all obvious where these circles are. So math has this wonderful ability to pop up again and again and again. And sometimes they say nothing as useful as a great theory. And why this is the case, why actually mathematics is the natural language of nature and it's able to speak to so many different topics, I think it is a miracle. Our brain has been trained to see everyday's phenomena, and therefore we develop math to capture that. But then you go into these unknown territories. You go to subatomic physics, or you go to the very edge of the cosmos. And again, the same mathematical equations are working. I think Wigner himself says it's a gift, and it keeps on giving. But we should be very, very grateful for that gift, because it allows us actually to address so many key issues in science using the same mathematical vocabulary.
And on radically different scales. I mean, that just seems remarkable.
It is remarkable that there is no kind of sign forbidden for humans once you enter the subatomic scale. Things that are very far removed from our intuition. And often I think it's actually the mathematical formulas that guide us. And if you ask me, what is an electron? And they're all images we have, of a little particle, of a wave. I think at the core, it is the solution to the Dirac equation. We haven't actually, I think, seen any circumstances yet, certainly in fundamental science, where math has not been able to guide us to solve the mysteries. Well, I think there's a continuous arms race between the progress in science and the progress in mathematics. And someone is ahead. Like, indeed, Newton had to discover, essentially, calculus in order to formulate his theories of mechanics. I think right now, certainly in terms of fundamental physics, the mysteries of quantum theory, they're kind of level. So we see that certain mathematics is extremely useful to understand quantum theory, but I think we all have a deep sense that still certain concept has to emerge, and that mathematics is in some way an environmental science. Now, if you move to these kind of esoteric areas of quantum physics, of cosmology, about space and time, we all feel and think that math is struggling, and that there are natural concepts that actually quantum physics suggests. To say one thing, like in quantum theory, everything happens in some sense at the same time. This is a wonderful phrase of a sum over histories. So, and sometimes said, anything that's allowed is obligatory, and it's all happening. So if you're a quantum theorist, you basically have to see everything at the same time. And that actually is also a natural language for mathematics to do so, because mathematicians want to study category of objects. But nature has found the perfect language to study these huge groups of spaces, of numbers. So what you see currently is that ideas from physics, from quantum physics, can be applied to very abstract areas in math, like studying knots, like circles embedded in 3 space, or studying the geometry of exotic higher dimensional manifolds. The most undervalued symbol in mathematics is the equal sign. Now, if you take a beautiful mathematical formula, it looks like A equals B. And often A and B come from completely different worlds. And physics and science is a way to produce these kind of equations. E equals mc squared, the most famous case. So you get these formulas, and then mathematicians look at it and, what are A and B doing in one sentence? These are completely different worlds, and you're bringing them together. And that gives a tremendous amount of excitement.
To Robbert, mathematics and physics feed each other, enhancing their explanatory powers. Each progresses by making deep connections, equating things that superficially seem radically different, but surprisingly turn out to be the same, thus enabling profound insights into the fundamental nature of things. Fine, makes sense. But specifically, how do the equations of physics articulate with the language of mathematics? And what does this say about the nature of reality? I ask a distinguished mathematical physicist at the Institute, a Fields Medalist in mathematics, string theorist, Edward Witten.
It's uncanny how powerful mathematics is in understanding physics. I think Eugene Wigner had in mind the fact that, on the one hand, to understand the equations of physics, you need to know a surprising amount of rather sophisticated math. But on the other hand, the equations of physics are mathematically interesting. So mathematics is the language in which the laws of physics are formulated, and in terms of which they have to be studied.
Why do you think it's uncanny?
Well, it's as if the universe had been created by a mathematician.
That goes into a whole other area that simple equations can work, even the inverse square law.
That wasn't fully understood until Einstein. So in Einstein's theory, you can't change the inverse square law. Newton could have used a different law, and he just took the inverse square from experiment. But in Einstein's theory, the inverse square is the only possibility.
And why is that the case?
Well, technically it's because Einstein's theory is a field theory. So there's no action at a distance between two objects. Rather, this one creates a gravitational field that this one sees. But the gravitational field of this one spreads in space. And because of the way the surface area grows as the distance grows, as it spreads in space, it falls off at such a rate as to produce an inverse square. So it's just a geometrical fact about 3 space dimensions that you get an inverse square law. So an example of why physicists considered Einstein's theory better than Newton's is that Newton could have changed the inverse square law, and Einstein couldn't. So Einstein, if you like, explained the inverse square law. Newton just postulated it.
What does that say about the nature of reality? I mean,
reality, as well as we can understand, is described by laws that are interesting and subtle mathematically.
So the unreasonable effectiveness that Wigner talked about was sort of math as the primary to explain the physical world, but you've done some work that goes in the other direction. There's some kind of common thing between the physics and the math.
There are differences in emphasis, in interests, in goals and focus. Math and physics keep intersecting because physical laws need mathematical structures for their formulation and also for their study. And those mathematical structures that play a role in physical theories are sometimes the most interesting ones.
What are an example?
A very early example was calculus, which is completely fundamental mathematically, but was invented because Newton needed it to describe the planetary orbits.
How about the work that you did that led to an elucidation of knot theory in mathematics?
We've all grappled in everyday life with a tangled piece of string, but most of us probably aren't aware that in the 20th century, mathematicians developed a rather deep mathematical theory of knots, which roughly speaking is a theory that describes all the way that that piece of string could have been tangled. And it has got many connections with physics. So even very early developments like the Alexandra polynomial. So he had no particular interest in physics, but later it was understood that the Alexandra polynomial can be naturally formulated in terms of quantum physics. Now, half a century or so after Alexander, von Jones discovered something called the Jones polynomial, a much richer generalization, which gave, if you like, more truths about how the piece of string can be tangled. And I had the good fortune of understanding how the Jones polynomial can be understood in terms of quantum theory.
And just what was that process?
I keep hearing uncanny, first by Wigner, now by Witten, to describe the astonishing power of mathematics for explaining fundamental physics. A striking example is the space-time geometry of Einsteinian gravitation. Reversing direction, Ed shows that ideas emanating from physics have led to remarkable novel insights in pure mathematics. I find this astounding. Math was meant to explain physics, but physics was not meant to reveal math. Do these bidirectional revelatory powers suggest hidden realities? I shouldn't get too enamored, because every physicist is not so awestruck by the primacy of mathematics. I speak with the author of Lost in Math, How Beauty Leads Physics Astray, theoretical physicist Sabine Hassenfelder.
No, I do not think that it is all that unreasonable that mathematics is effective in the natural sciences, because what is mathematics about? It is a way to describe patterns, to describe regularities, and that's exactly what we do in the natural sciences. So there is, of course, an underlying question here, which is, why is the universe such that there are patterns for us to discover to begin with? And I think that that's a question which just falls outside of science. Personally, I think that the more interesting question is, why is mathematics so inefficient in the other sciences? Like if you look at social sciences or maybe also neurobiology and related disciplines, there's very little mathematics that is actually being used. In physics, all our theories are mathematical, but that's not the case in other disciplines, which brings up the question whether that is a property of nature. Is there just a limit to what we can do with mathematics? Or is it just a case of we have not yet found the right mathematics?
Well, trying to explain these larger phenomena in biology and psychology and then sociology, you have a multiplicity of variables which you don't have at the physics level. But I think there's a deeper question. Why are the patterns in nature such that many of them have a unity of specificity that describe the pattern? So it's not a question that there are patterns, but there are patterns that are susceptible to very simple mathematics.
Well, again, you could argue that maybe we have only been able to find the patterns that we can describe with simple mathematics.
I think the question of patterns, though, at the deep physical reality is still a problem to me. I don't know why any of the fundamental aspects of reality should submit themselves to simple mathematics unless there was some deeper kind of relationship, which is why the unreasonable effectiveness resonates with me.
I'm always afraid that in the end, a kind of discussion will just lead to some anthropic statement of the sort that if those laws would not be so simple, then we would not be here and we wouldn't have been able to find them, which ultimately does not explain anything. I see myself not so much in the business of trying to understand why those laws are the specific laws that describe the universe, but more concerned with the question, does it work? And for me, if
Sabine says, follow the science. Just see what works. Don't be infatuated by abstract notions of mathematical beauty, simplicity, other fanciful ideas. Science searches for regularity, and math describes regularity. So what's the big deal? Math, Sabine argues, works where it works and doesn't where it doesn't. Nothing unreasonable here. So, is the effectiveness of mathematics and the natural sciences unreasonable or not? Maybe it turns on what we mean by unreasonable. I speak with a physicist and science writer who sees a larger landscape for science, Leonard Mlodinow.
Leonard, would every physicist think that the effectiveness of mathematics is unreasonable?
That depends what you think is reasonable. It certainly is impressive, it's exciting, it seems miraculous. You know, nobody really knows, and everyone has an opinion. It's a subtle question because physicists use math, they misuse math. Quite often, physicists, especially in their quantum field theories, for example, the theories of elementary particles, we use these kinds of operators that are poorly defined, or we don't quite understand how they're defined mathematically. There's all these infinities that we have to get rid of, and we just find our ways of doing it. So in my opinion, why is it so effective? You can describe things, of course, using language. Mathematics is much more precise than language, because built into the mathematical language that you have are rules of logic and reasoning. So when I write a sentence, as I do when I write books, I can make the next sentence anything I want. When you write a first sentence of mathematics that you have really restrains where you're going. In fact, more than restrains it, you might have to spend hours working out where it's going, but it's going somewhere and it's just going there. It's not going anywhere else because the logic of the situation is built into the equations. So mathematics is a way of precisely describing things in a way that the logic and the answers are all built in, and it's just up to you to extract them. It's not really why it's so effective, but it's a justification for why it might be. The deeper question is, why does nature behave that way? Who says nature should be logical? Who says the same thing should happen every time? On the most fundamental level, things are ordered and well-defined, and they follow very simple mathematical laws, and it is like a miracle. If you don't believe in God. If you believe in God, you have an answer.
Len sees mathematics as a language constrained by rules of logic. But why, at the most fundamental level, do very simple mathematical laws work, in his words, so miraculously? To scout out a possible reason, I meet the author of Our Mathematical Universe, who claims he has an answer, MIT physicist Max Tegmark.
I think the question of why mathematics is so unreasonably effective, it's just gotten more and more pressing and embarrassing over time. I mean, if we think back to Galileo, he could use math to effectively describe how a hazelnut and a grape would move if he threw them, right? But he could not use math to figure out why one was green and one was brown, or why the hazelnut was hard and the grape was soft. Yet later we got Maxwell's equations, which showed how you can figure out light and colors with math, and then the Schrödinger equation of quantum mechanics, which told us how you can figure out properties of material, like hard and soft, etc., with math. And then we got the standard model of particle physics and the standard model of cosmology. And by now, we have been able to apply math to almost all aspects of our physical reality. And Why is that? There's a spectrum of answers. I have a number of colleagues who dismiss it as just a fluke. They're like, math is just a useful bag of tricks we've invented that's sort of approximately helpful, but we should be grateful for it and not talk more about why. And then you have a lot of my physics colleagues who feel that math is somehow a useful, approximate description of our world, even though our world is still fundamentally somehow non-mathematical. And finally, on the other end of the spectrum,
Where you sit.
where I sit, I have this very extreme view, taking sort of Platonism to the extreme. I think that the reason math has been so effective in describing the world is that the world is mathematical, completely mathematical. We actually inhabit a mathematical structure. And the approximations we've found so far are just some simpler math approximating, the actual math. And this sounds completely crazy because, I look around myself in the world here and like, where's the math? I don't see any giant numbers written in the sky or whatnot. But if you look a little closer, there is math all over the place. For example, the largest number of fingers I can put that are all perpendicular to each other is 3. That number is very built in to the fabric of reality. We have a nerdy name for it we made up in physics. We call it the dimensionality of space. This property of space is this number, 3. And if you look at all the elementary particles that make up everything we see right now, what properties does an electron have, for example? Well, we discovered it has the property -1, 1, 1/2. And we've made up these nerdy names again for these properties, like electric charge and spin and lepton number. But those are just words we humans made up. The properties are just those numbers. And more shockingly, the only difference between an electron and an up quark and a photon and all the other particles that we have around us here are what numbers their properties are. So if you start to take seriously the idea that both space itself with its dimensionality and curvature and topology and other mathematical properties, and all the stuff in space, all these particles have, as far as we can tell, no properties at all except mathematical properties, then it starts to sound a little bit less crazy that maybe it's all mathematical, and maybe this is why math has been so useful for us.
How would you know whether the equations you're working with are the real fundamental aspects of reality or are approximations?
There's been a major injection of humility in physics, which I think is welcome. Steven Weinberg loves to say that every single equation that we're taught in our textbooks, we should view as probably just an approximation of something deeper.
Would there be any flashing neon that would say that you've really got at least one equation that you could say is fundamental? How would you even know that?
That's the curse of physics. Mathematicians can prove that something is true. In physics, you can never prove that a theory is true. The big neon light flashing that we generally look for is the light that flashes and says, error, theory seems wrong. The way that might happen for this meta theory that it's all mathematical is if you discover that there's some physical world phenomena that really can't be described by math. The main candidate, get that red light flashing, is consciousness. Yes. And even with intelligence, we've progressed leaps and bounds, where we can now have machines that can beat us at the Asian board game of Go, and so on. And we're realizing that the reason for this is that intelligence isn't something mysterious that can only exist in biological organisms. It's ultimately just the mathematical theory of information that counts. Consciousness is the last holdout, which we have still been really, really stumped by. But the prediction I'm making that it's all mathematical will be falsified if you find just one aspect of the world that you can't describe with math.
How to understand math's unreasonable effectiveness. Unreasonable or not? Math and physics feed each other, making deep connections. Ideas emanating from physics can inform pure mathematics. Could this surprise be a clue to the deep structure of reality? Not every physicist calls the effectiveness of mathematics unreasonable. Math just works where it works in physics, while in other sciences, math is not so effective. Math is a language constrained by logic, but that it works so well seems a miracle. Could all reality literally be math? I like Max's bold vision, though I fall short as a believer. I also like his challenge to falsify his vision, especially with consciousness. Eugene Wigner ends his essay with wonder. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. Of this I am quite sure. One way or the other, math's unreasonable effectiveness gets us closer to truth.
For complete interviews and for further information, please visit closertotruth.com.